In this tutorial, we're going to talk about the graphs of exponential functions. So the first thing that I want to talk to you about is the effects of a certain parameter. Keep in mind the original, or the general formula for exponential functions is f of t equals a times b to the t. So what happens to exponential functions if a changes? Let's take a look. Okay, so let's take a look at these three functions. The first one being 150 times 1.2 to the t, and then 100 times 1.2 to the t, and then 50 times 1.2 to the t. So notice that the b, or in this case the growth factor, since that number is greater than 1, is greater than 1, and it's all the same. They're all growing at the same rate. The only part that's different here is the a term, or the initial value. So notice in these functions that this guy matches its y-intercept. And that will always be true for exponential functions. So here's 100, here's its y-intercept. Here's 50, there is its y-intercept. So that's all the effect does from that a parameter. So what happens when b is different? Let's take a look at that. Okay, so here we have four different functions, all of them having a as the same number, and notice that its y-intercept, all of them are that number, 50. So the first two functions that we're going to look at are these ones over here going upwards. The f of t equals 50 times 1.4 to the t, and then times 1.2 to the t. First, I want you to notice that these are both growth factors because they're larger than 1. So both of these guys should be going in an upwards fashion. And they are. And since 1.4 is larger than 1.2, its function should be increasing at a much steeper and quicker rate than this guy. The next two, notice, are less than 1. They're growth factors, so these are not growth, these are decay. So instead of these functions going upwards, they should be going downwards towards the x-axis, and they are. Now, notice that 0.8, it seems like because that number is greater than 0.6, that it should be steeper. But keep in mind that because this number is 0.8, that means that a function is decaying by 20%. And this one, it means that a function is decreasing by 40%. Because 100 minus 20 gives me 80%, or 0.8. And then 100% minus 40% gives me 60%, or 0.6. So it does make sense that this bottom function is steeper than the other. So this guy should be steeper, it should be decaying faster than this guy here. So that's the effect that parameter b has on our functions. Now, one way to describe what these functions do over a long period of time is called a horizontal asymptote, and what we're going to start looking at is how to use what we call limit notation. So I want to first of all just discuss what that is in general, and then we'll take a look at how to do that with an example. Okay, so this is what we call limit notation, and I'm going to walk you through this little bit by little bit, so don't freak out if it looks confusing. This part here is LIM, which stands for limit. And the part on the bottom, this x and then the arrow to infinity, means as x approaches infinity. In other words, as my x values get larger and larger and larger towards the right-hand side of my function. F of x stands for whatever function that you may have. It may not be exponential, it could be anything. And k stands for the value that my function is approaching as I get closer to infinity. Now, on the other hand, I could do the same exact thing as my function is approaching negative infinity. Now, in terms of exponential functions, this guy over here, as x approaches positive infinity, well, this is going to be for decaying functions. This guy over here is going to be for growth. So here's how we say this. If you look at the decay limit, if I were to say this all in one big swoop, I would say the limit as x approaches infinity of f of x is equal to k. Or the limit of as x approaches negative infinity of f of x is equal to k. You have to start becoming very comfortable with how to say that because you're going to see it in calculus. All right, now let's take a look at just a very quick example. I'm going to go ahead and just briefly sketch out a decaying function. So let's say this is my guy. All right, and we will call him f of x. So what I want you to notice is we want to try to figure out exactly what this k value is going to be for these kinds of functions. Now, as x approaches infinity, well, that just means as x gets bigger and bigger and bigger going this way, because infinity is all the way out here in Foreverland. So what's going to happen to this function as this guy gets closer and closer and closer to this? Where's that function going to go? Where, in terms of the range, or the y value, is that going to get closer and closer to? And the answer is this. It's going to get closer to 0. Look at where this guy matches up on the y-axis. It starts up here for this guy, and then over here it's here, and then as you just keep on going, it just gets farther and farther and farther down the line and closer to infinity, and the y value is closer to 0. Another way of thinking about that is if you're decaying by a %, let's say it's bacteria and it's decaying, and you keep having it, and you half it, and you half it, and you half it every single day, are you ever going to completely run out of that bacteria? And the answer is no. Not according to these formulas anyways. But we're going to get very, very close to 0. So what I would say here for my answer in terms of this function, what is the limit as x approaches infinity of this function? I would say that it's 0. And it doesn't have to touch it. It just needs to approach it because it's saying as x approaches infinity. Where is it getting closer and closer to? And my answer is 0. So that's something else that we're going to start looking at is limit notation. And this is called also called a horizontal asymptote. An asymptote is very simply an imaginary line that your function will never ever touch but get extremely close to. And that is going to conclude it for this tutorial.